welcome back. So we are discussing LED, light emitting diodes. You remember in the last class I had introduced the concepts of efficiencies, external quantum efficiency and wall plug efficiency, which are very important terms in LED. We derived the expressions. I told you that wall plug efficiency is always slightly lower than external quantum efficiency, and most of the LED manufacturers will try to quote wall plug efficiency only, because that's what you're interested in, how much optical power you're getting divided by how much electrical input power you're supplying, right? That quantity stays, the definition stays valid for all kinds of LED, whether it is visible or UV, IR LED and so on. I told you about heterojunction, why heterojunction is important, and different kinds of LEDs that are there. Today we shall discuss a little bit on the loss. What are the losses in LED? Because extracting light out from LED is a very important task, and it is not very obvious that you will be able to get all the light out because of many loss mechanisms that take place. If time permits, we shall also go through some electrical properties of LEDs, which is essentially a PN junction, a diode kind of a thing, but there are certain aspects in LED that we have to take care when we are discussing a PN junction. Okay, so we will come to the whiteboard here. So we have discussed the efficiencies, and if you recall the last lectures, discussed the efficiencies and then also the recombination, the bimolecular recombination rate, and I had discussed how the excess carrier concentration is there important, and for high level and low level injection, the internal quantum efficiency is given by the ratio of the the non-radiative and radiative lifetimes sort of thing. So all these things we have covered. So today we shall discuss about an important thing, and that is called the losses. Okay, extracting light out from an LED is actually a quite difficult task. I mean, if you have an LED, you will definitely be able to see it glowing. If you have a blue LED or a red LED on a wafer of gallium nitride, a blue LED on a gallium nitride wafer or a red LED on a gallium arsenide phosphide wafer, you will be able to see that there is a red glow or a blue glow with your eye, but that is only a fraction of the light that is emitted. You actually lose out a lot of the light. So one of the very important loss mechanism, you will see very well, is that suppose you take a case where this is your semiconductor. It can be GaN, a gallium arsenide, anything. Okay, it is your semiconductor and this is your air. Okay, this is a semiconductor, this is your air. So if you think of light coming out from here, from any of the point here, then there is a critical angle, because there is a refractive index difference. This is a refractive index of n naught, this is refractive index of say ns. So when the light comes out, within a critical angle, from high school physics, that it can come out with an angle of refraction like that, right? There will be a the angle here, and then there is an angle of refraction here. The angle of refraction is larger because the refractive index of air is lower, right? So at a particular critical angle, theta c, your light rays will get total internally reflected, and above that your light ray will get bounced back inside. It will get bounced back inside, right? So only those light rays can come out of the semiconductor crystal which are emitted within this angle of theta c, the critical angle, because all the light rays emitted otherwise will basically get bounced back within the crystal. And then this is, I am talking about the top emission. You can also think of side and edge and other emission, but essentially you are going to get emission within only a cone. Okay, and that's called escape cone, because the light can escape only within that cone. You see my point? This is your semiconductor and this is your air. Because of this mismatch in the refractive index, a light ray can only come out within this angle. I mean, this angle is theta c, this angle also is also theta c, of course. So if you talk about a 3D visualization, this is a 2D, but if you talk about 3D visualization, then this whole thing will be like a cone. That's called your escape cone, because light can come out only within that cone. Okay, all the light that is emitted at angles higher than that will actually bounce back within the substrate itself. So that's a huge loss that you have actually. You recall that this critical angle is equal to sine inverse of the refractive index of air by refractive index of the semiconductor, right? And if this quantity is small, then you can almost write it as refractive index of air by refractive index of semiconductor. Okay, so you will see that actually for typical gallium arsenide, for example, or gallium phosphide, for example, these numbers, this refractive indices are around 3.6 or 3.5. So gallium nitride also is maybe 2.5 or so. So the critical angle will be around 16 to 18 degree. What it means, degree. What this means is that your light will be able to only come out within that angle. So there is a large amount of light which cannot come out ever because of this total internal reflection. That is a huge loss actually for your light, right. That is a limiting mechanism for your light, right. So even if you have a wide band gap semiconductor on a PN junction, even if you have a wide band gap semiconductor like that, this is not the absorption when the photon, electrons and holes emit, recombine, the photons that is emitted, the energy of the photon is less than the p type or n type layer. This absorption, the photon will not get absorbed in this layer. That is different from this refractive index. Refractive index is, this is air, this is whatever. So at this interface it will get this refraction, no. So total internal reflection will basically limited. Okay. So there is a loss, and that escape cone loss, will basically set a limit. It will set a limit to the efficiency you can achieve, okay. So that is a very sad thing, because now you will lose a lot of light out there, and so you call this efficiency of OP, that is the optical loss due to this critical angle, due to this total internal reflection, okay, because of light travelling from one media to another media. So essentially you can think of this as the efficiency that is limited is that light is coming out within that cone, right. I told you there is a cone there, right. The light can only come out through a cone. After that light will not come out, after that it will get bounced back. So light will come out through this cone. So this cone basically is a solid angle. In a 3D you do not talk about single angle, you just talk about solid angle in steradian, if you remember your 10+2 maths. So essentially that efficiency limited by this escape cone, because most of the light will get reflected within inside and lost, a very fraction of this will come out. This is basically defined as the ratio of the the solid angle. It is defined as the solid angle of that cone, okay, solid angle of the cone divided by the total solid angle of a 3D, which is 4 pi steradian. Remember, this is all in steradian, by the way. 4 pi steradian is like the solid angle of a complete sphere, like in omnidirection. Just like in a 2D, if you have a circle, then the angle of the circle is 2 pi radian. Do you remember that? 2 pi, 360 degree, no? This is 360 degree, which is 2 pi. Similarly, in 3D, in a spherical thing, you can think of the total solid angle as 4 pi. So this is the solid angle of the cone with which the light escapes. This is only the light that will contribute to a light coming out, and then this is 4 pi is the total solid angle. It so happens that you can do the math here. The math can be done, and this comes out, this NOP comes out to be around half 1 minus cos of theta c. Theta c is the solid angle of the the critical angle of the semiconductor, right. So this NOP, the efficiency limited by the total internal reflection, is half 1 minus cos of theta c, okay. That is the limitation you will get actually. And you can, if this theta is very small, then you can do a Taylor series expansion. A Taylor series expansion can be done. If you remember your maths from your 10+2 and maybe your undergrad first year, you can do a Taylor series expansion to do some approximation. If theta c is low, then you will get NOP as equal to 1 by 4 refractive index of air divided by refractive index of semiconductor whole square. This is your efficiency that is limited by the escape cone, okay. This is the efficiency that you will limit by escape cone, okay. And then if you take a planar structure, if you take a planar structure like that, this is your LED, for example, this is just like a planar structure, okay. If you take a planar structure and that light is coming out and getting reflected, whatever, then there is an emission pattern. Light will come out in certain pattern, no, that is called emission pattern. Emission pattern. In what pattern is the light coming out? Because everywhere light will get emitted from each and every point, right. And so if you look at that angle theta, then you can say that the total light power, the intensity that is emitted is equal to the power that is emitted by 4 pi r square. R is the distance from the the wafer, you can say, point, and this is n naught by ns square, the refractive index square, into cos of theta naught. The angle theta naught is the angle at which you are looking essentially. In a way you can say that this is the emission pattern, and the typical emission pattern is called a Lambertian emission pattern, okay. Lambertian emission pattern. This is the pattern of emission of light from a planar LED. Okay. Lambertian emission pattern will come. Now this is a huge loss, by the way. This efficiency that you are getting, there's a huge loss that is because of total internal reflection, and most of the LEDs are planar. You have a wafer which is a plane, right? It's not like a whatever thing. It's a plane, and because of the planar wafer, if you look at a 50 or 60 degree angle, your intensity will drop by maybe 50%, for example. Okay. Now, how do you beat this problem? This problem of total internal reflection that is killing your wafer. What you do is that this total internal reflection will not take place on a spherical surface. Suppose I have a point light here. Then no matter whatever direction the light goes, any direction the light goes, what will happen? The surface of a sphere, if you draw a tangent, the tangent is always perpendicular to this radius, no? At any point the tangent is 90 degree, and if it is 90 degree, then absolutely there will be no total internal reflection. It will come out straight. There will be no problem. So what you do, of course, it is impossible or almost very difficult to make a gallium nitride or gallium arsenide wafer which is spherical like this. So what you do is that you have your wafer. This is your P gallium nitride. This is your indium gallium nitride quantum well. This is your N type gallium nitride. Suppose blue LED. What you do is that you put a hemispherical coating like that. This is a hemispherical coating. There is a hemispherical cap, you can say hemispherical encapsulation. Okay, hemispherical encapsulation of a material whose refractive index of this hemispherical encapsulation, Ne for example, is suitably adjusted so that you get minimum total internal reflection even with 90 degree here, so that there is no the perfect sort of thing, and you will essentially able to extract out light better. So this hemispherical encapsulation is of course given in commercial LEDs, so that you are not able to lose you do not lose the light because of total internal reflection, right? It will eliminate your critical angle limitation. So you put a hemispherical coating, and this could be any polymer or any other kind of material that people can suitably figure out based on the application. And apart from this loss, there could be also other loss. In terms of, so light extraction is a very complicated business, efficient light extraction. There is another loss, and that loss is called Fresnel loss. S is actually silent. Fresnel, you might have seen the Fresnel refraction. Whenever light travels from one medium to another medium, there is a loss because of reflection at the interface. Light is coming out, even if it is coming out perpendicularly, there is a fraction that will actually come out, a small fraction might get reflected. So the Fresnel the loss is basically about a mismatch in the refractive index, and so there is a reflection that takes place. This reflection coefficient, the reflection that takes place here, can be said as semiconductor refractive index minus the air refractive index to which it is going, whole square divided by semiconductor refractive index plus air refractive index whole square. Okay. So this loss, this is a this quantity is reflected. So whatever intensity you have, this fraction of that, this fraction of this quantity can be say 20%. If you put say Ns of gallium arsenide is 3.4, so what you can do is that the amount of light reflected at the interface of gallium arsenide and air will be 3.4 minus 1, air is the refractive index of 1, 3.4 plus 1 whole square. So this is 2.4 by 4.4, which is almost like 1 by 2, which is square is 1 by 4. So you can say that almost 25% of the light is reflected unnecessarily. I mean, this is not unnecessarily, but this is something you cannot control. So this is lost basically. Whatever intensity you are putting, of that 25% is lost because of Fresnel reflection. There are ways to actually reduce it by doing some kind of surface texturing, making the surface rough, anti-reflection coating, and all these things are more of the technologies associated with light extraction. Okay. So those are important things that we should be aware of generally. And then an LED is an electrical device, of course. So these are the loss mechanisms I have talked about. I'll quickly tell you about LED as as an electrical device. So I told you that an LED, if you can simplistically think of this as a PN junction, the forward bias current, even if it is a quantum well, there will always be a forward bias current, right? It can be quantum well, multiple quantum well, double heterojunction, who cares? They will always be there, right? So if you have silicon, for example, if you take just a silicon PN junction, it is not an LED, by the way, you will have a forward current like this, and this cut-in voltage is probably around 0.7 volt, right? Then if you take gallium arsenide, and the cut-in voltage will be around 1.2 volt, right? You can take probably in gas, you can take in gas, it can be also less than that, because it can be less than silicon in gas photodiode. You can take maybe InGaN green LED. A green LED would probably be here, InGaN green LED. The cut-in voltage would probably be around 2.6 volt or so, and then there is a blue LED, that is the blue LED InGaN, classic blue LED, that would be around say 2.8 volt, maybe 3 volt, depends how good it is, right. Deep UV LED, I couldn't show it here. Deep UV LED, okay, a deep UV LED would be much more, maybe 5, the scale is not correct, maybe 5 volt. At 5 volt only the UV will turn on, or 4.5 volt, because the band gap is also high answer. So what you see here is that to get the same current, say this is 20 milliamp, 20 milliamp is a standard, that's why I keep mentioning that, 10 milliamp, 30 milliamp and all. So to get say 20 milliamp of current for a lower wavelength light LED, blue, green and all, you actually have to apply a higher voltage to get the same, because this cut-in voltage, all this cut-in voltage depends on band gap Eg. So if your band gap is large, which means the emission wavelength is low, as you go lower and lower wavelength, green, blue, near UV, deep UV, as you keep going shorter and shorter wavelength, you are going larger and larger band gap. What happens is that you need to spend more energy, you have to bias at a higher voltage to get the same current, injection current. To get same injection current, you have to go to a higher voltage, you are losing more, actually you have to apply more voltage. That's why you have to apply more electrical energy, that is one thing. To get a UV or a blue LED, you have to apply more electrical energy input than getting, for example, a red or a orange yellow, right. And if you talk about this, what is the voltage, if you have a constant area, if you talk about all the devices having the same area, so that there is no problem with the normalization of area. If I say 20 milliamp ke liye, for 20 milliamp of current, how much is the voltage that I am dropping, okay, as a function of band gap. So on the x axis I have band gap of different material. So I have a band gap of 1 EV, band gap of 2 EV, for example, band gap of 3 EV, band gap of 4 EV, band gap of 5 EV, and this is the voltage. On the y axis is the forward voltage drop. This voltage drop, this is turn on, but I will talk about this voltage drop. This voltage drop at 20 milliamp, what is the voltage you are dropping here, okay, what is the voltage you are dropping for different LEDs. So I will call this the forward voltage drop at 20 for getting 20 milliamp of current, okay. So this is 5 volt, 4 volt, 3 volt voltage, 2 volt, 1 volt and 0. Ideally it should have been a linear line, like almost like a linear line, like that. So 1 to 1 correspondence, 2 volt ke liye you get 2 electron volt and so on and so forth, but actually it's not so easy. So your in gas will have a band gap of 1 if you are emitting at 1.3 micron, it's probably less than here. So you will in gas get here, this is in gas, so it's less than 1 electron volt the band gap, and you also drop less than 1 volt to get 20 milliamp. You have gallium arsenide at 1.4 EV, at around 1.4 EV, your band gap is 1.4 EV, you also have to drop around 1.4 EV to get the 20 milliamp, because cut-in is typically low. For gallium arsenide cut-in voltage, the turn-on voltage would be 1.2 volt. For silicon it might be 0.7, 0.8 volt, but the band gap is 1.1 volt. So at 1.1 volt you might be getting actually 20 milliamp of current, you following my point, right. But the problem is, these are almost on the line, but the problem is with green and blue, okay, with green and blue, the problem is you will have to go much higher. For example, if I take about red and orange, they will be in the range here only, all will be here 2.3, not 3 actually, sorry, ideally it should be like, this. So all your orange and yellow and everything will be hovering around this point, 2, 2.1, 1.9 and all this red and all, right. But the moment you talk about green and blue, you are going to have a little problem. So blue actually it will be here, you should ideally get 2.8, the band gap should be 2.8 or 2.9 electron volt, but you are in fact dropping more than 3 volt, for example, to get the same. Similarly, Algan at 4.5 volt, you should be able to get this 4.5 EV band gap, but the voltage that you have to drop is more than 5 volt here. So typically 3 nitrides, for 3 nitrides the voltage that you have to drop is actually more than the band gap, equivalent band gap by Q, okay. unlike L gas, N gas and all. The problem is because there is a problem, there is in LED there is always a delta EC, delta EV because of the heterostructure. These are called band discontinuities and these are large in 3 nitrides, smaller in L gas gas. That is why when you inject current, these also play a role. Okay, these will limit the thing, and also 3 nitrides have a poor hole doping. It is very difficult to dope them whole. You do get hole doping, but the hole doping is very inefficient. That is why the first demonstration of successful hole doping led to the invention or the development of high efficiency LED, which is why they got the Nobel Prize. This hole doping is still very challenging. It is done, but it is very poor. It is not 100% ionized. So that is one reason, and because of this poor hole doping, your hole injection is very difficult or very poor. And as you go higher and higher band gap, L-GaN for UV, deep UV, your p-type doping becomes worse and worse, and so your hole injection suffers more and more, and you have poor p-type conductivity, poor p-type contact. This is why you have to apply more voltage than what is needed theoretically to get the same input this milliamps of current. Okay. Now this is of course generic LED that I was talking about, but I mean this is about the PN, but electrically there is also another important thing to understand. You see the idea, it is basically a PN junction. Even if there is a quantum well or a double heterostructure, it's eventually a PN junction diode that you can explain the equation. So you can say that the diode equation holds true, ideal diode equation, which is I equal to I naught exponential of QV by eta or n kT. This is Boltzmann constant. This is of course ideality factor. If you remember, ideality factor tells you how close to ideal diode equation your device is. If your ideality factor is 1, it means it is an ideal diode. If it is 2, it means even it is deviating, it is recombination dominated. I told you in gallium nitride LED you can even have 3 or 4. If you have not done it well, it can be even 10, 20, that is terrible. If for for gallium nitride, yeah, if the material quality is not good, your ideality deviation will be there, and you will have a large ideality factor. Now ideally a diode should be able to, this is a LED of course, ideally a diode should be able, you can schematically you can say this is the diode, but the problem is that there is always some series resistance. What is series resistance? Series resistance is all the parasitic resistances in the contacts in the neutral P and N region, right? Those are extra voltage that you will drop there. So this is a series resistance that comes, and then there is a shunt resistance that comes. Shunt resistance is always in parallel. It basically is it's the dislocation or any other parallel leakage path, surface leakage. Like you have this LED wafer, suppose this is your LED wafer on which you are making many LEDs here, but the current will be top down, flowing top down. Actually, as I told you, the way it looks like is that this is your P GaN, for example, this is your quantum well and in GaN and other things, this is your N type GaN. You basically make a contact on the top P GaN, typically with nickel and gold contact. This is a metal. Then you etch down in dry etching. In plasma chemistry you will etch down and you will come to N type GaN and you make a contact here, which is typically titanium and gold. When you apply voltage and this contact, then the current will flow, and essentially the emissions will come out from here, the quantum well, right? The quantum well will emit. So this is like a structure here. The current has to flow vertically, but the material quality of gallium nitride and such kind of things is not so high. So you have a lot of material problems. So you have dislocations going like this from the substrate. This is some substrate that you have to grow. Sorry, okay, I have clicked on something else here. Yeah, so you have many dislocations coming out. These dislocations are basically missing line of atoms. These are crystal imperfections and defects, and because you grow on some substrate like sapphire or whatever, right, there is no native gallium nitride substrate easily available. So because of these dislocations and all, you can have leakage through these dislocations even if you don't apply, even if you have a reverse bias. Ideally your device should not leak, but it will leak because of these dislocations. These are like parallel paths. You can think of these as like parallel leakage paths that will always occur. That is captured by this. Ideally you would like this to be infinity. That means the parallel path should have infinite resistance, which means they should not be there. That means the top down current should be dictated by the diode behavior, not this parallel path. So you want this infinite, you want the parallel paths, the leakage paths to have infinite resistance, which means current shouldn't flow them, and you want the series resistance to be 0 so that no voltage unnecessarily drops across this series resistance or the contact resistance here, right? This is a useless voltage drops that you will have otherwise, right? Now the question is, how will the ideal diode behavior change in an LED in the presence of this series resistance and the shunt resistance? It's important to know in general because we are discussing LED here. So ideally I told you, this is your I versus V. What happens is that ideal diode equation should look like this, right, and then it should look like this ideal diode equation. But in the presence of this thing, what will happen is that your extra series resistance will dominate. No, if your series resistance dominates this extra series resistance that you are dropping, then of course this is your ideal, this is your ideal, then series resistance will dominate, so it will increase the resistance like this, it will go like this. This is your series resistance dominating, and this series resistance typically starts dominating when your voltage is high and you are having a large voltage drop across the series resistance, this excess parasitic resistance, it will look like that. Okay, it will not affect the reverse bias, forward bias will be affected, you will get low current at the same voltage, say 3 volt or 5 volt, you are supposed to get this value of current, but instead you will get lower current because of the series resistance. And now what about the shunt resistance? Shunt resistance is a parallel leakage path. So what it does is that it increases the leakage, it increases the leakage. Even on the forward bias, it will screw up your turn on, it will go like this, okay, which is very bad. It will screw up your turn on and you will have essentially a premature turn on, you will have a premature turn on, right, a premature turn on voltage and a higher reverse leakage, higher reverse leakage. So these are the characteristics of your shunt resistance, RP, okay, shunt resistance. So those also affect your devices bad way, okay. So if you look at the circuit now, you can actually find out these are PN junction things only, but in the context of LED I am talking about, because you will see that in practical LEDs these are important. So if you look at this circuit again, this is your series resistance, this is your diode, right, and this is your shunt resistance RP. Then if you have a current that is going here, right, there is a current that is going here, some current will go through the diode, some current will go here through the parasitic resistance, they will again combine here and flow out here as I, right. So you are actually applying a voltage here, your voltage is applied here because this series and shunt resistance will always be there, right. So if this is the current that is flowing here and this is the voltage you are applying, then the voltage that is dropping here is given by I times Rs, right, that is the voltage that is dropping here. So the voltage at this point A will be given, the voltage at this point A will be given by V minus IRS, right, that is the voltage that is at this point, right, of course. So V minus RIS, so this voltage actually between A and B, the voltage between A and B that is dropping across the diode and across this shunt resistance is actually V minus IRS, and this V minus IRS, if you divide by RP, which is this resistance, then you get the current flowing through here, which is IP, right, you get that current, right. And your diode equation, if you recall your diode equation, pure diode equation, it is actually the diode current that is flowing here, I diode, is equal to I naught, which is the reverse saturation current, e to the power what, e to the power the voltage that is dropping across the diode, which is nothing but this quantity, right. So that is Q, this quantity, okay, V minus IRS by eta KT, okay. This is your current that is flowing through the diode. So essentially what's happening is that the total current is equal to the current flowing through the shunt resistance, which is IP, plus the current that is going through the diode. So the total current is equal to IP is this, which is V minus IRS by RP plus I naught reverse saturation current exponential of Q, of course Q, V minus IRS by N KT. Can you see the point? Let me write it down again. The total current that is flowing minus V minus the total current IRS by RP, series resistance and shunt resistance. It is our, we want to find out the series and shunt resistance. This is your I naught, the saturation current, reverse saturation current, e to the power Q V minus IRS by eta KT, okay. This gives you the modified diode equation in the presence of series and shunt resistance. This is your modified equation of the diode, right, in the presence of series and shunt resistances, because RS and IP are there, right. And you can actually find out this series and shunt resistances RP and RS, can be found out from this equation by doing some fitting and other things. We will not go into that right now, but you can actually find out the series and shunt resistance from this equation if you do a fitting and you do some derivative and other things. Okay. Those are part of the advanced syllabus. We will not cover them right now here. So, what we will do is that we shall wrap up the lecture here. We are almost done with most of the important aspects of LED, the electrical properties, the efficiencies, the escape cone losses and other things. There is a small portion of LED remaining that we shall try to cover in the next lecture, and that is about the LEDs that are visible, which our eye can sense. Then we talk about brightness, colors, color rendering and chromaticity and other things. We shall try to briefly discuss those in context of white LEDs or LEDs that can emit light that are perceptible to human eye. Okay, that because then that is a human eye related thing. So, we will talk about that a little bit, and then we have few more lectures on transistors. We are again coming back to transistors on different aspects. Okay, that is the final concluding part of the course. Transistors for high speed application, transistor for high power applications, logic, memory and so on. We shall go through them little carefully so that you are aware which applications need what kind of transistors and what are the materials, what are the technologies needed for that, what are the figures of merit, how do you compare one category to another category and so on. Those should be a part of the curriculum, because that gives you an idea and calibration as to what kind of devices are used in the different applications and electronic gadgets that are around you. Okay. So, let us end the class here, and the next class we shall quickly touch base upon some of the LED aspects with respect to visible LED. Okay. Thank you for your time.